Method of sections. So what is that method? Now, method of joint, if you went through homework assignment, you'll see sometimes can be very frustrating. Sometimes you want to find an internal force or some external force at a specific member, and you don't want to start from the joint that meets your requirement and go joint by joint to get to that member, uh, to find that specific force you're looking for, or unknown force. A method of sections is going to help you a little bit with this. Right? The whole idea is that, as we said about the method of joints, and when we're talking about joints, if the truss is in equilibrium, right, which is the main assumption we make in this course, and that's the big assumption we make, like everything is in equilibrium. If the truss is in equilibrium, then any segment of this truss is also in equilibrium. Right? So if I just consider this truss with so many members, if I just cut part of this truss, right, take part of this this truss structure, take it out and isolate this from the rest of the structure. In method of joints, that part was just a joint. In method of sections, I'm talking about one part of the whole truss, including a couple of members and joints. So every section should also be in equilibrium. And that's the underlying, I guess, assumption, or the main thing you need to know when it comes to method of sections, and how does that work, if you want to know, I would say. That it starts from here, that if the truss is in equilibrium, any segment of the truss is also in equilibrium. Now, what we do in method of sections, as the name kind of insinuates, that we can make a cut or make a section and expose, or the members that we cut through them, right, instead of having internal forces, now they are going to have external forces, right, because they are the members that are exposed. So pretty much we expose each internal force as an external force, or we turn it into an external force on our free body diagram for that specific section. Now, once we have that section with all the forces, we can actually write the equation of equilibrium. And we can afford, as we know, in two-dimensional space, of a rigid body equilibrium for two-dimensional space. We know we can afford three unknowns. So let me put a few words here before getting into details. So let's start with the main, I guess, opening line that I just said. If the truss is in equilibrium, right, then any segment of the truss structure is also in equilibrium. Right, that we know. This is something we're sure about. Now, as I said, we can make a cut or section and then expose each internal force in the truss or those members that we cut through. And basically, once we have this portion of the truss, we can write the equation of equilibrium. So let me write it like this. Or just for you to have it, when, or let's put this way, we can make a cut or section and then treat each well, let's put this section and get and divide, this is better, and divide the truss structure into parts, into parts that are basically, each of them is a rigid body, rigid bodies. Right. Now, let's put it this way. When we cut a truss, when we cut a truss, we can write the equation of equilibrium. That's not how to write equations. Equations of equilibrium for each section, and find the forces. And in two-dimensional space, well, I'm just talking about, let me write it here. Summation of forces is equal to 0, or maybe I shouldn't write it this way. Since it's two-dimensional, I'll just write the 3 equations. You can afford 3 unknown, right? Summation of forces in x direction is 0, summation of forces in y direction is equal to 0, and summation of moments about some given point is equal to 0. So we can afford 3 unknowns. Let's take a deeper look at what I'm trying to say here. Let's say I have a member, a truss, like this. I'm going to try to draw it as good as I can. Like this one goes there, from here. This is connected to this joint, obviously. And then let's add another part. Let's also make a member here. And here we have one joint there. This is a pin support. And let's call this, just put a roller there. If I want to put names, let me follow the notations I have. A, B, C, or maybe not exactly. That doesn't really matter. C, D, E, F, and G. Let's assume that we have all the dimensions, and we know how the members, the dimension for each member. And let's say I want to find the force in internal forces or internal force in member BC, or internal force in member GC or GF, any of these members. So how do I use method of method of sections? If I want to use method of joints, if I want to find the internal force in member BC, I have to start from A, and let's say we have also a force applied to this. You have some external force. I have to start from joint A and go one by one, go find these two first, and then use the method of joint, or write the equation for joint B and find the force in member BC. Now, what if I want to go directly? I want to not go joint by joint. I want something faster, right? Something that I can just go directly to member BC and find its internal force. Now, I make a cut. I make a section. I say I'm going to cut the truss from here. And let's call this cut, I don't know, I guess AA. Like following line AA, doesn't even have to be distorted, just some general line. I cut this. Now, if I do this cut, let's see what I get. I get 2 separate bodies, right? One side, I'll get this. If you look at the left side, I'll get this, something like this. This is there. And then I have members that are like this. let's say I'm following the cut line, and this is there. This would be A, and the force is there. This is B, and this is G. Now, if you look at just this section, this is, I cut the truss, and we have two sections, one on the right, one on the left. Right, you separate them. If I look at the one on the left, I have an internal force in BC. Now it's exposed. Right? It would be FBC. I have an internal force in GC that now is exposed, so it becomes an external force. And one in GF is also exposed. Now these internal forces, that's what I was trying to say, that these internal forces turn to external forces. And this structure, this cut, should be in equilibrium. So from here, you can afford having three unknowns, right? This is a rigid body in equilibrium. You have, assuming that you have this force, some force applied here, FA. Let's call it FA there. All you have to do is to use the equations of equilibrium, right? Summation of force in x direction, summation of force in y direction, and find the moment about some point. You can find FBC, FGC, and FGF. And this is the FBC would be the internal force for member BC. So by cutting that, I got that part and looked at it as a rigid body in two-dimensional space. Same story about the other side. Let's see what happens in the other side and what can we get out of that. And this side, we get this part. Then I get this part. Right. This part is there. I get right here. This one goes there. This is there. This is there. This is there. Now, if I isolate that part, keep in mind that I still have supports on that side. So I have to take into account those supports. This is probably dx. Let's just choose some direction. It's just dy. I have a roller there. So this is ex. Assuming that this is x and this is y. And these are the points. This is d. This is e. This is f. And this one is c. So we have the forces in our members. Right. This would be F BC. This would be F GC, and this would be F GF. So this is another rigid body, right? Rigid body with multiple forces. Now the problem with this one though is that I have more than three unknowns, right? So if I want to use this side, right, the first side, I could just easily write the equations since I only had three unknowns, right? Three unknowns. So I was fine. But here I have three unknowns. Let's say I don't look at the section from the left. I look at the section from the right. You can choose whichever section you want when you make a cut. On the right side, the section from the right side, right? This one has three unknowns. If you want to start with this one and you want to find the internal forces in members BC, GC, and GF, you have three unknowns, those forces. Now that they are external forces, internal forces, because I made the cut. And you have forces from the support reactions, which you don't have. So this is not, you can't go about solving for those unknown forces, internal forces you wanted by just this. You had to start it from one step before. Can someone tell me what should you do if you want to use this section specifically to find these forces, FBC, FGC, and FGF? Do you have any guess? Because in this state, right, this is, I call this section 2, and this is section 2. I call this section 1. I made a cut and I got two sections. What would be the approach if, I mean, in this case, it's easy to go with section 1. But what would be the approach if I wanted to make the cut and use section 2? Do you have any guess? because I have more than 3 unknowns there. I'm sorry. I have more than 3 unknowns there. At the moment equation to get your other unknowns. Thank you. Thank you, guys. Well, I do need to write my uh, moment equation, but I have to start it from one step before. Like I have to take one step back. I'm really sorry, guys. I have to take one step back. Thank you. And I have to look at the free body diagram of the whole structure, right, before making the cut. Because right now I have too many unknowns. If I make the cut, I have FBC, FGC, FGF unknown, and then support reactions unknown. I can take one step back before making the cut, use the free body diagram of the whole structure and find the support reactions. Once I have support reactions, then in this cut, I only have 3 unknowns, because from the rigid body diagram for the free body diagram for the whole structure, I can find dx, dy, and ex. Then once I make the cut, and assuming that I can't use section 1 for some reason, I can use section 2, because once I make the cut, then support reactions are known from my analysis of the whole rigid body, finding support forces and moments. So I can use that, and then, so let's put it this way: if you get to know dx, dy, and ex from the free body diagram of the whole structure, then you can use this section to find move things around, to find F, BC, FGC, and FGF, right? Then you can actually do that. All right, this is a general idea. I wanted to get a sense of what is going to happen when we look at an example. I'll look at a couple of examples this week, and you will see how this whole process works. But just get a general idea of what happens and how does the section work and what comes out of it, and how can we actually analyze it using rigid body, whatever we learned when we were studying equilibrium of rigid bodies in 2-dimensional space. Now, one thing that we actually still have to mention is that the direction of the forces. Remember, that was the kind of challenge when we were using method of joints. We said, well, you have to use inspection, figure out if it's under tension or compression. Do your best to figure out as many as you can. Sometimes you can afford having multiple direction unknowns. Sometimes you can only afford having one. Typically, we can afford having one. And in some cases, by just looking at the free body diagram, you could figure out if you have 2 known forces with known directions, the other 2 should be in a specific direction. Otherwise, they don't cancel each other to be in equilibrium. But there was the whole process, depending on what the case was. Now here, the same problem. When you make a cut, I just put FBC, FGC, and FGF in those directions. But I didn't do any inspection or any checking, right? So how do we figure out the directions? We are not starting from a specific joint. It's not as easy to do inspection. Sometimes you can still do it, get a sense of whether that member is under tension or compression. But the good thing about this method or approach is, about there are good things and I would say not bad things, but different challenges related to this method. Direction is less of a problem. You can just make an assumption. You can use inspection to figure out what is the direction of force. Or you can just make an assumption that assume that all the unknown member forces are at the cut, at the section you're making the cut, or at the part that you're making the cut in your I would say cut, the cut section, or in tension. Always go with the assumption. If you don't know, like what I did here, I said all these members are under tension. Then eventually you're going to get the number, and the number would be positive or negative depending on whether you get positive, you made the right assumption. If you assume negative, you made the wrong direction, and you have to switch the direction of the force. So that's less of a problem. All right, let me just mention that here. So how to determine the direction of the forces in this method. It's specifically for method of sections. So two approaches. One, well, like before, by inspection. Two, always assume that unknown members or unknown member, right? Member forces, the forces related to those members, or let's put it this way, at section, at the cut section or in tension. You can always make the assumption if you don't want to deal with the whole inspection process and figure out how what is the correct direction of the force.